So, good evening, everyone. Can you hear me?
Good evening, sir. Yes, you're
Yes,
audible.
sir.
Okay, fine. So, I'm SK Nitish Murugan. I'm a second year PhD student in the Department of Mechanical Engineering, IIT Madras. So, recently I got selected for PMRF. So, I will be handling the strength of materials for you. So, let's get started. So, can somebody help me with how can we actually give auto entry for every participant so that I should not have to do admit at every time? Since this is my first class, like I couldn't able to get.
Sir, that facility is not there in Google Meet, sir.
Oh, oh. So every time I should give admit all.
Yes, sir. Yes, sir.
Okay. So can
Because
you?
uh,
Yeah.
because you are the host, no, sir. That's why you have to do all that, sir.
Okay. Okay. Okay.
Hello, Murugan.
Hi. Yes, bro.
Yeah, yeah. You can do one thing. Go to the setting.
Yes. This is the settings, right?
Yeah,
Host
setting.
controls.
In setting, you go to the general tab.
General tab.
Yeah, yeah. General. There is an option. Google uses these system logs to make Meet better.
Oh,
Correct.
one
Oh,
1 minute, bro. Set.
no, no. That is not that option. I
Yeah.
thought
Set.
that. Yeah,
Yeah.
yeah.
Settings is there.
Hmm. No, no. That
Okay.
is not the option. I thought it is the option. It is showing something different.
Okay. Okay. Fine.
Yeah, yeah, yeah.
So every time I
Yeah.
have to give admit all. Okay. Fine. No issue. Okay. So let's start with the class. Because only issue is like I have to give admit all to everyone. Okay, we will wait till one more minute and then we will start. Okay. Actually, this should be turned off. There is only quick access. Okay, Chrome extension for this.
Sir, can I ask a question?
Yeah. Yes.
Sir, are you from which college, if you don't mind?
Yeah, I'm from IIT Madras, bro. I am doing my second year PhD.
Okay.
Yeah.
Good evening, sir.
Yes. Good evening, bro.
Sir, I'm going to ask you a little bit off topic,
Yeah.
maybe not relevant to standard material, but relevant to mechanical engineering. Can I ask?
Yeah. You can go ahead.
Sir, I have zero knowledge over GT. I mean, group task. How
Okay.
to start and where from I will get all relevant materials, because in coming day probably HPCL I will get chance in HPCL GT round.
Okay. Regarding that, I don't have any idea, bro. Sorry.
Okay, okay, sir.
Yeah. So let's get started without wasting much of time.
Yes, sir.
I have installed this thing, but still it is showing me. I don't know.
Hello, sir.
Yeah.
This session videos offline video available, sir.
Yes, bro. It will be available offline. Actually, I am recording it, so it will be available offline.
Through YouTube only, sir.
Yeah, through YouTube. Yeah.
Thank you.
Okay, then let's get started. So, again, good evening, everyone. I'm SK Nitesh Shimurugan. I'm a second year PhD scholar in the Department of Mechanical Engineering from IIT Madras. So hereafter I will be teaching you strength of materials, and in today's class we will be seeing about the introduction to stress and strain, and the properties of materials, and then the 3D representation of stress and strain, and then about the uniaxial loading and triaxial state of loading. Okay. So this is the tentative course plan. In week one, which is this week, we will be seeing about introduction to stress and strain and the properties of materials like that. And in the next week, we will be seeing about axially loaded members. And the next week, we will be seeing about shear force and bending moment diagrams. And further, we will be seeing about bending. Hello. Can you please, if anyone, I request you to turn off your audio so that it won't disturb us. Yeah, and in week four, like we will be seeing about bending and shear stress in beams, and then we will be seeing about torsion of shafts, and then we will go to principal stresses and strains, and then we will see theories of failure, and the 5 theories of failure we will see, and then we will look on deflection of beams, and then thin cylinders and spears, and then we will conclude it with theory of columns. Okay, and so let's get started. So the first thing is I want to discuss is with you is like what is the can anyone tell me the difference between engineering mechanics and strength of materials?
So the
Yes,
mechanics
sir.
is
The basic difference is that in engineering mechanics, we deals with rigid body, and
Yeah,
system material deals with deformable body.
yeah,
Up to certain level, deformation is allowed.
yeah, fine. So why we actually need a separate subject called strength of materials to study deformable bodies?
Because sir, in rigid body does not exist in nature.
Yeah,
It's a
fine.
hypothetical body.
Yeah, fine. So the basic definition of a rigid body is as follows. Like for example, like how can we define a rigid body is like this. For example,
Uh,
I
two
yeah,
things there. Any 2 point in between a body will remain same, whatever the condition is applied on the outside.
yes, that's correct. So the basic definition of rigid body is like the relative displacement between these points or any point in a body actually remains the same irrespective of the type of applied load. Okay.
Yes, sir.
So this or this distance, the relative distance between 2 points will actually remain the same. Whereas for a deformable body, the relative displacement actually changes after the application of load. Okay. So this relative displacement, this actually changes after the application of load. Okay. So in engineering mechanics, we would have learned the effect of forces like equilibrium of forces, then moments, then centroids, and then a moment of inertia, and the effect of force like displacement, velocity, acceleration. Whereas in the strength of materials, we will be studying about the resisting forces due to the externally applied loads. Okay. So here I've given the stress. Here I will be showing the stress strain curve for the rigid body. Okay. So it actually even after the application of loads, even whichever higher value of stress we are giving, there is no strain induced in the rigid body. Okay. This is actually the strain. Okay, and this is actually the stress. And sorry about my handwriting because this is the first time I'm using the writing pad, so later I will get accustomed to that. Okay. And the this is the stress strain diagram for a rigid body. Okay. And for a deformable body, if you take the stress strain diagram, will actually be something like this. We will
Like,
be having
is
yeah
this course related to semester or gate?
yeah, gate.
Gate na, because at gate 2023 na.
Yeah, GATE 2023. Yes, bro.
Okay.
This is actually just a brief introduction so that we will get into problems soon. Okay.
Okay, sir. Okay.
Yeah. So for a deformable body, the stress strain diagram which will actually look like this. Okay, and it will have its own plastic hardening or strain hardening. And coming to the what is meant by homogeneous and isotropic material, anyone?
Sir, homogeneous means property will remain same in particular direction, and isotropic means property will remain same in all the direction.
Okay, with isotropic, you are correct. Whereas for homogeneous, it will be like irrespective of the region of space within the material we choose, same
Sir,
properties will be there. Yeah,
homogeneous is make materials having same properties means same particles.
yeah. At different particles, like we will be having the same properties. Okay.
Same properties with different particles, sir.
Yeah, different particles. So for example, imagine this is the material. Okay, so I am taking a point here, and then if I see the Young's modulus or the shear modulus or any kind of property, the same property exists at a different point. Okay, for example, even here I could for example, here the Young's modulus value is E, means at a different point also the Young's modulus value will be the same E. Okay.
Yes, sir. Yes, sir. I have wondered if the
Yeah,
material is different, Young's modulus will be the
definitely,
difference for
definitely,
that.
if the material is different, definitely this is for a particular kind of material. Okay.
So this is for homogeneous material.
What, bro?
Okay, okay, okay.
Okay.
Sir, if we come to same material, the elastic constants will be same, no, sir.
See, for same material, the elastic constants will be same. That is the assumption we are making, which is homogeneous assumption.
Okay, okay, sir.
Okay. Whereas for example, if you take a material, there are some defects which are available in the material, and due to some kind of manufacturing processes, also you cannot get a homogeneous material all through the space. Okay. So the due to some kind of manufacturing processes also, like you will be getting some non-homogeneity in the material. So due to that only we are making the assumption in strength of materials, like we will be dealing only with homogeneous and isotropic materials. Okay. So
Okay, sir.
this is about the homogeneous material. So whereas for the isotropic, as someone pointed out, like isotropic,
Is a directional dependent property.
yeah. So at each, for example, at a single point, if I take the properties remains the same in all directions. Okay. So here I have taken
What
the
about if the property is different in different directions, sir?
that we will term as the anisotropy, which the
Okay,
material we will
okay.
term it as an anisotropic in nature. Okay.
Okay, sir.
Yeah. For example, this is the anisotropic material. Here I will show. For example, I am considering a single point, and in this point, with respect to different, with respect to different directions, the material property changes. Okay. For example, when I look in the x direction, it would be E1, whereas in the other direction, it will be E2, and in the other direction, I will have a different Young's modulus value. Okay.
Sir,
So,
Yes, sir.
yeah.
sir, will you repeat the homogeneous concept?
Yes, yes, bro. So in homogeneous, actually, what is the a point is like, for example, at each point within the material, within a particular direction, okay, the value of the Young's modulus or the value of any kind of material property remains the same.
Okay, okay, get it, sir.
Yeah.
Yes,
For
sir.
example, I have shown you here. Okay. For example, I have taken numerous points within the material, and for each point, the in a particular direction, the Young's modulus value remains the same.
Okay, okay, get it, sir.
Yeah.
Get it.
So this anisotropic properties will also be induced in the material during its manufacturing process. For example, you would have known this manufacturing process known as additive manufacturing. So in additive manufacturing and all, like we will be depositing the material layer by layer. So in that, what happens is like in the deposition, in the build direction, the properties varies when compared to the in plane direction. Okay. So there and all, this anisotropic is a big problem with respect to the manufacturing process, or with respect to the additive manufacturing process. Okay. So here we will see about what is the combined effect of homogeneous and isotropic material. Okay. So here, in whichever point I take, or in whichever direction I take, all through the space of this material, the value of Young's model, or the value of the property does not change, irrespective of the point as well as irrespective of the direction. Okay. So which means, like, for example, for a particular material, the Young's modulus and or the any kind of material property remains the same. Okay. So let us see before. Then let's go to the next slide. So coming here to the concept of stress and strain. Okay. So first of all, like, stress is actually nothing but, yeah.
Sir,
Yes. Yeah.
sir, can you tell us about orthotopic materials?
Orthotropic material is nothing but, see, for example, in anisotropy, with respect to different directions, for example, in at a point you can have infinite number of directions, right?
Yes.
So at infinite number of directions you will be having different properties, whereas for orthotropic, maybe here I will show. One minute, there is some problem with the point. Yeah. So for an orthotropic material, the value of Young's modulus will be the will be different in 3 mutually perpendicular directions. Okay. For example, take XYZ as the 3 mutually perpendicular directions. The value of the Young's properties will vary across these 3 mutually perpendicular directions alone. Whereas for isotropic, like, we can have an additional direction here. Is it fine?
Okay, sir.
Yeah. So coming to the concept of stress. So stress is actually induced only when a body is constrained with respect to its to a particular direction. Okay. For example, here I am taking a prismatic bar and I am loading it in the x direction. Okay. So imagine this bar is not constrained. So what will happen when I load this? It will actually start to move, right? So only when I constrain it, then these stresses are induced in the material. Okay. So actually the stress is denoted by force by area, which is here in this case P by A. Okay. And strain is given by epsilon, which is nothing but the change in length divided by original length. Here change in length can be denoted as del L divided by the original length L. Okay. And then there are basic differences between, there are two terms called engineering stress and engineering strain, and true stress and true strain. Okay. So engineering strain, for example, when we are having a specimen and then we are loading it onto the UTM machine, which is the universal testing machine, for analyzing the stress strain curve of a particular material which you have developed, imagine. So the first thing which we will try to do is, like, to obtain the stress strain curve of the particular material. Okay. So for so after loading the material onto the UTM machine, the the calculations which are like, for example, the engineering stress is defined as the load by the original area A naught. Okay. Whereas the true stress, which is denoted by sigma T, which is equals to the load, applied load, divided by the instantaneous area AI. Okay.
Sir, someone would like to join into the class.
Okay. Yeah. So the true stress is actually nothing but the force divided by the instantaneous area, or the load divided by the instantaneous area. Okay. And then whereas the engineering strain, which is denoted by here, say E, we can denote engineering strain by E. E is equals to change in length divided by original length, whereas the true strain, or here I will take this as epsilon itself, whereas true strain I will denote it by epsilon t, which is nothing but the instantaneous change in length, which is denoted by dl divided by the original length. Okay. So why we actually going for true stress or true strain is like, during the metal forming operations, we are actually dealing with plastic deformations. You have heard about this term metal forming, right? Where we will be working with the materials so that we can plastically deform the material to obtain the desired shape of the material. Okay. So there and all, this true stress or true strain concept is very important. So in order to get the relation between what is the relation between true stress and true strain, we will go with sigma t is equals to P by AI. Okay. So based on volume consistency, the volume of material before and after deformation remains unchanged, right? For example, if I start with the initial cross section as A naught and the initial length as L naught, and the instantaneous area, which is AI into Li, this will be the volume, right? So this volume is actually conserved during the deformation. So this AI can be replaced as A naught L naught divided by Li. So sigma t will be equal to P into Li divided by A naught into L naught. And this P by A naught can be replaced with sigma or sigma naught, which is the engineering stress, into Li divided by L naught. Okay. And this Li is nothing but, or the instantaneous length is nothing but L naught plus the change in length, which is nothing but delta L divided by the original length L naught. And this can be written as sigma naught into 1 plus del L divided by L naught, which is nothing but del L divided by del naught is nothing but the engineering strain. Okay, which is 1 plus epsilon. Okay, so this is the relation between engineering stress and true stress. Similarly, we will see the relation between true strain and engineering strain. So here true stress is given by dl divided by L, and if I integrate with respect from L naught to the final length or the instantaneous length Li, we will get ln of Li divided by L naught. Okay, and this ln of Li divided by L naught can be written as L naught plus del L divided by L naught, which is the original length. So this again can be replaced as ln of 1 plus del L by L naught is again engineering strain. So the these two relations between true stress and true engineering stress and true strain and engineering strain is very important, based on which, like, you will be you can get questions in 1 mark or 2 mark. Okay, so this is fine, right?
Yes, sir.
Okay,
Can you
sir.
kindly repeat for the relationship between engineering strain and true strain?
Yeah, again I have to repeat the thing between engineering stress and true stress. Okay,
Engineering strain and true strain.
engineering strain and true strain. Okay, see, true strain is actually defined by this term called dl by L, which is nothing but the change in instantaneous change in length divided by the original length. So instantaneous change in length is always represented by dl by L. Okay, so, and for example, the initial length of the bar, let's take it as L naught, and it has gone to the instantaneous length of Li. So what I'm doing is like I am integrating here from L0 to Li so as to find out the true strain. Okay, so this is actually nothing but ln of L, and I apply the limits from L0 to Li. So what I will get at the last is ln of Li divided by L0, and this instantaneous length Li can be replaced as the original length L0 plus a change in length delta L. Okay, so ultimately what I will get is like L0 divided by L0 will be 1 and delta L divided by L0 will be the engineering strain. So the final relation is like true strain is equals to ln of 1 plus engineering strain. Okay.
Got it. Thank you.
Yeah. Then let's see the stress strain curve of the mild steel material. So mild steel is the most widely used material, and similarly for example here first thing what I am doing is like I am taking a tensile specimen according to the ASTM standard with this dumbbell shaped specimen. Okay, and then I am loading it onto the UTM machine, and then I am applying a tensile load. Okay, so this you all know. I will just refresh this concept so that like it will be a continuation. So the first thing what happens here is like first we are loading the material from we are giving a small amount of load. So for the given amount of loading there is a small deflection. So this deflection goes on continuing, and up to a certain limit, like the stress is directly proportional to the strain, and this limit up to which the stress is directly proportional to strain is known as the limit of proportionality or the proportionality limit. Okay, so limit of within this limit the stress is directly proportional to the strain. Okay, and after this within a small distance when I keep on continuously loading, there will be a point which is termed as the elastic limit, wherein like up to this point whatever the deformation which is happening after unloading, we can actually regain the original shape. So that is termed as the elastic limit. So this is of particular this limit is of particular interest for structural engineers. Okay, structural engineers always works within this elastic limit or the yielding limit, because like structural engineers, for example, their only objective is to design a structure so that it does not yield under the current loading conditions. Okay, and after the elastic limit we are having the upper yield point, and this upper yield point and the lower yield point is only specific to mild steel, because you can see here the serrations, right? This is actually due to the quadral atmosphere which is actually generated inside the mild steel specimen. For example, the quadral atmosphere is nothing but the dislocations actually moves, and then it stays in one at near the grain boundaries, and once if we give further loading, again the dislocation starts moving, so like that. So there is a continuous drop and rise in the value of stress during this region. Okay, but for design purposes we will be taking this upper yield point as the yield stress value for mild steel. Okay, and then after this region, like we will be having the strain hardening region, wherein like we have to give more stress from here from the onset of upper yield point, plastic deformation happens, which means like after for example after loading and unloading we won't be able to get the original shape of the material. Okay, so what happens is like after the lower yield point, and even if we are loading the material, what happens is like the stress values continuously increases on with the increase in the strain values. So which means like to deform the same material, I have to give more value of stress or more value of load. Okay, and this continues to happen up to a point called ultimate strength, wherein the this is the maximum value of stress that can be that a material can be subjected to. Okay, And after this, what happens is like necking starts to occur. Necking means, like, for example, this cross-sectional area, it actually drops to a very tiny value. Okay, so necking starts here, and then ultimately the specimen breaks, so which is known as the fracture point. Okay, so this region, this plastic region, is actually of interest to metal forming processes. Okay.
Hello, sir.
Yes, bro.
Sir, why the stress value is going to decrease after ultimate stress?
Yeah, this is actually nothing but, for example, after the this is only specific for mild steel. Okay, in mild steel, what is the interstitial impurity we have in the form of carbon atoms, right?
Then
Okay, so
carbon atoms provide the ductility property is more, no, sir.
what?
When we come to the carbon property, the ductility will be more, no, sir.
Yeah, ductility will be more for sure, but we can't say also, right? Because, for example, for cast iron, the percentage of carbon is high, whereas cast iron is brittle also, right?
Yes, sir.
Yeah.
When we come to the this one
Hello, sir.
mild steel stress strain curve,
Yeah.
Hello, sir.
Yes, bro.
there is a statement called 1 minute, bro. There is a statement called if the 50% of the 50% of the less than length, it is called as ductility, sir. Is it true or false, sir?
No. See, actually, that's a kind of measure they can actually attribute to. But what is actually meant by ductility is like how long it can permanently deform without any fracture. That is the measure of ductility. For example, if you are taking here the mild steel stress strain curve, here you can see at this point only the material fractures. Whereas for brittle material, without showing any permanent deformation, it actually fractures at without giving any warning. Okay.
Sir, what is mean by yielding?
Yielding is nothing but getting a permanent deformation. That is termed as yielding. Okay.
So E to F is as well permanent deformation of the date.
E to F is actually permanent deformation. Like when you unload, you won't be getting the initial shape.
So it is like after yielding, we term we term E to F also as plastic deformation.
Yes, whatever the deformation which occurs after the yielding point, we term it as the permanent deformation or the plastic deformation, because you are not going to get the original shape.
Sir?
Yeah.
Hello, sir.
Yeah.
Sir, as up to the yield. Hello.
Yes, bro.
One minute. Sir, up to the ultimate stress, we are increasing the value of means applied load, no?
Yeah. Yes,
But
bro.
after that, our loading condition is the same one, but there is a stress is going to be reduced. How it can be possible? Like force upon initial area is written as a stress,
Yeah,
but even though its
see,
value
actually,
is going to decrease.
Yeah, see, what you are saying is correct. Actually, the true stress value goes on increasing. Okay. The true stress value, which is calculated based on P by AI, which is the instantaneous area. This instantaneous area actually reduces after the maximum strength. Okay, which is the ultimate strength. Okay, this actually reduces. Okay,
But
so
sir, what is happening in engineering stress? Like why the value is showing as
yes, actually, what happens is like in the UTM machine, the loading value actually drops after the ultimate tensile strength. Okay, so due to that only this P by, which is the original area, the engineering stress is always calculated based on original area, right?
Yes, sir.
So the original area is actually we are retaining the same value. So what happens is like the loading condition or the load value decreases after the ultimate strength. So due to which the engineering stress or engineering stress graph it falls below.
Like you are saying, like the body is experiencing less force during that period, so that's
Yes,
why
body
this
is
is
actually
being happened.
experiencing less force only due to a reduction in the cross-sectional area. Okay, for example, if we are taking this reduction cross-sectional area into account based on the given value of load, then the stress value will be something up to here. It will follow this path.
Okay, sir.
Okay.
Okay, sir. Thank you, sir.
Yeah, whereas you are making the calculations based on engineering or the original cross section alone, it seems like the stress value actually falls after the ultimate strength. But truly what is happening is like the area of a cross section actually reduces, due to which the applied load actually reduces. But the final output is like the true stress, which is sigma t, actually increases. Okay.
Okay, sir. Thank you.
Yeah.
Thank you.
So let's proceed to the next slide. So in this slide, we will see about additional terms called modulus of resilience, modulus of toughness, allowable stress, and creep. Okay.
Sir, from B to C, what occurs? After elastic limit up to upper yield
Okay.
point.
See, after here B to C is actually shown to be exaggerated. Okay. B to C is actually very much near to what we see. Okay. See, actually, C is actually B is actually the point wherein, like, even after the removal of load, like, we will be getting the original shape. Okay. Whereas C is the point where the after the removal of load, like, the material actually starts to deform. Okay, so we won't be able to get the original shape. But the length of this B to C is very small. But here it has, in this figure, it has been shown to exaggerated. Okay.
But actually, they are like one single point only.
Not one single point, we can say, like, they are very close to each other. For example, like, in terms of a difference of 10 megapascal or something like that.
Yes, sir. So the behavior need not be studied that significantly.
That significantly, yes, bro.
Sir, can you differentiate and say about difference between upper yield point and lower yield point? That
Okay, this upper
that
yield
deflection
point,
C, D, E.
yeah, okay, fine. C is the upper yield point. Okay, so when we are actually elongating the or deforming the specimen in the UTM machine, what happens is like the stress curve comes up to here. Okay, the stress values comes up to here, which is the upper yield point. After this, for mild steel alone, there is a significant drop in the yield point after the initiation of the upper yield point. Okay, so this point D is termed as the lower yield point. Okay, and this happens only for mild steel.
Yes.
So, for all the structural applications, like, we will be using only the upper yield point, so that it is very safe. Okay.
Yes.
Okay. So coming to modulus of resilience. Resilience is actually nothing but the amount of strain energy absorbed by the material within the elastic limit. Okay, that is termed as the modulus of resilience. For example, here you can say the as I told you already, right? Already, like the elastic limit and the upper yield point is very close to each other. So the strain energy or the strain energy absorbed by the material is always given by the area under the stress strain curve. Okay. Okay, so this area under the stress strain curve is actually nothing but the strain energy absorbed by the material. And here we are taking within the elastic limit, which means like more or less equal to the yield point. So if we can write modulus of resilience as
Hello, sir.
Yes, bro.
Sorry to interrupt, but I have a question. Like, which one is the best representative of stress inside the body? Like, true stress or engineering stress?
Yeah, true stress is the best representative, I should say, to my knowledge. Okay, whereas because it only gives the actual stress which is existing in a material. But for engineering applications, everywhere you could see we will be using only engineering stress, whereas true stress only comes in the metal forming operations. Okay.
Yes, sir. Yes.
Okay. So here, if we are taking the area under the curve within the elastic limit, for example, you imagine, let us take up to this, which is, we will term it as sigma y, which is the yield stress. So you can say this is the epsilon value. So can you say what is the area under this curve, or the area in the shaded part? It looks almost like a triangle, right?
1 by 2 sigma epsilon.
Yeah, 1 by 2 sigma epsilon. Yeah, 1 by 2 sigma y into epsilon. Okay, so from this is
This
actually
is per volume, sir. This is per volume.
Yeah, this is per unit volume. Yeah, this modulus of resilience, this is actually per unit volume. Simply, if you are saying the resilience means it is the what to say, the total strain energy absorbed within the elastic limit. But if you are saying modulus of resilience means it is actually a property of the, it becomes a property of the material, because you are dividing it per unit volume. Okay.
Sir, one doubt, small doubt.
Yeah.
So resilience is the total energy and modulus resilience is per volume.
Yes, total energy per volume. Yeah.
Okay. Thank you, sir.
Yeah.
Sir,
Yes, bro.
the difference between proof resilience and the modulus of resilience, sir. Sir.
Proof resilience.
Yes, sir.
Okay. Actually,
Sir,
there is a term
1 minute,
called-
sir. One
Yeah.
question. There is one question. I'm actually BTech student, second year, sir. From I have joined diploma. I have joined BTech through diploma, sir.
Okay.
Where we have studied that modulus of resilience and proof resilience are determined due to energy resistance in the beams or in columns.
Okay.
Amount of energy used for resistance for loads.
Okay. Okay.
Is that true or?
See, actually, what is the meaning of modulus of resilience is like, for example, let us imagine a spring. Okay. Consider this as a spring. Okay. So what does a spring does? After I am loading it, and when I'm removing the load, it actually regains its original shape, right? So
Yes, sir.
how much of energy which is absorbed by the spring within, because spring we can consider it as an elastic member. Okay. So the amount of energy or the absorbed by the material within the elastic limit is termed as modulus of resilience, which means how much energy can it absorb. That can be as a measure of the modulus of resilience.
Then for unit volume, na, sir?
Yeah, per unit volume is
Yeah.
actually I mean it becomes a property.
Okay, sir.
When you multiply by the volume of the material, then it becomes the total energy stored in that body.
Yes.
Okay.
Okay, sir.
So coming to this proof resilience, actually I'm not quite sure about that. Maybe I will look into it and I will say it in the next class. Okay, is it fine?
Yes.
Okay.
Yes, sir. I know, sir. About proof resilience, I know, sir. Can I?
Yeah, you can say.
Sir, proof resilience is the nothing but energy stored which resistance the load. When we come to modulus of resistance, it is divided by unit volume. That is the difference, sir.
Okay.
Sir,
Yeah.
sir, I want to add one thing.
Yeah. Yes.
Like proof resilience comes into the picture if like a material does not exhibit the proper yield point. So we talk about the proof resilience based on the
No,
concept
that is
that we
ultimation.
take.
No, this is also correct, I guess, because proof
Like
word is
no,
always
sir.
used. Yes, bro.
Yeah, the proof word is always used when the material
there is-
does not exhibit a proper yield
Yeah.
point,
Yes.
like aluminum or other materials. are there.
Yes, bro. Yes.
So that's why it is same as resilience, but
Yeah.
it's term when the
When the material
material does
doesn't
not
have a
exhibit.
significant or a definite yield point, like we can term it as a proof resilience.
Yes, sir. This is
Yeah.
the concept.
Yeah. Thanks. And then let's go to the measure of toughness. Okay. What is the meaning of toughness of a material? Toughness is
The area under the curve of stress sensor is called
area
toughness.
up to the fracture limit. That is very important. Okay.
Fracture limit, yes, sir. That is the important.
So up to this fracture limit, what is the area, full area, that is termed as the toughness of the material. Okay. And if you are dividing again by per unit volume, that is termed as modulus of toughness. Okay.
Yes, sir.
Modulus of toughness is actually nothing but up to fracture point. Okay, the area under the stress strain curve, but per unit volume. And then let's see about the allowable stress. What is the meaning of allowable stress? Anyone?
Excuse me, sir.
Yeah.
Sir, kindly tell me the formula for modulus of
Sir,
toughness.
it is the
Yeah, for actually for modulus of toughness, we can't give any formula because the shape of the curve is very arbitrary, right?
Yes, sir.
So what one thing what we can do is like we can find an average stress value, and then based on that we can find the area under the average stress value.
So, sir, the measurement of modulus of toughness based on the area
Yes,
area of the curve, right, sir?
area under the stress strain curve. Yes, up to the fracture point.
Yes, sir. Thank you, sir.
Okay. Another, I heard another one person asking doubt.
I was actually answering allowable stress. I think it is actually after considering factor of safety, the stress the material is allowed to undergo.
Sure.
Like,
Yeah, correct. Yeah. So allowable stress is nothing but, as the person rightly pointed out, allowable stress is equals to failure stress divided by, we will always give some factor of safety for this. Okay, the factor of, why we are actually giving for factor of safety is like, for example, during manufacturing itself, there can be some defects which are induced due to the manufacturing process. So for that, we will always give some factor of safety. Okay. So this failure stress divided by factor of stress is always the allowable stress or working stress. Okay. And this failure stress for ductile materials, can you guess what will be the failure stress for ductile materials?
Sir.
If you are actually designing a structural member?
I think it will be yield stress divided by factor of safety.
Yeah.
It should be less than.
Yeah, for ductile materials, it will be yield stress divided by factor of safety.
And for brittle, it will be like, I think it will be UT, like
ultimate strength, yeah, divided
ultimate
by
stress.
factor of safety.
Sir, how this factor of safety is calculated?
See, it's based on what to say, experience only we can say, bro. When we are actually designing a component, at first we will be giving some 2 or I mean we can give some more factor of safety, for example 4, 3 or 5, like that. But based on like our experience in that particular field, then we can actually optimize the factor of safety. But at first we will give a very high factor of safety, and for critical applications we will give more factor of safety also.
So I have a very small question. So, sir, if we are increasing FOI, that means the cost will increase.
See, actually, increasing FOIS doesn't mean
Like,
we are actually
like material will be like like we
Yes,
are
sir.
not using
The
material
cost
to
will
the full
increase.
potential.
See, one point we can say is like since we are actually working with less kind of stress, I mean we are actually, the allowable stress is actually very less when we are actually increasing the factor of safety. Then what we need is like we have to actually support with more material. Okay, so maybe due to that we can actually come to the conclusion like cost actually increases. That can be one viewpoint.
Because, sir, I was thinking that since we are giving more FOS, that means the material is not being used up to its full potential.
Yes,
That's
definitely.
why I thought the cost will increase. Like we have to put more thing.
Definitely, that's what. See, for example, when you are having when you want to work with more factor of safety, then ultimately what you will do is like you will be supporting the or the loading conditions with more material, right? So ultimately what happens is it adds to the cost.
Thank you, sir. Thank you, sir.
Yeah. Then coming to the creep. Creep is actually nothing but permanent deformation which occurs under constant loading conditions. Okay. And it actually requires some time to actually exhibit the permanent deformation that is called creep. Okay, for example, I'm taking a member, a prismatic bar like this, and I'm actually applying a tensile load on this. So after some years or after some days, what happens is like there will be some kind of plastic deformation to this member. So that property is actually termed as creep. Okay, and this is actually time dependent.
Sir, 1 minute. Sir, there is statement called what you have said is right, sir. But without any load or without any force, how the plastic deformation will be held within the days?
No, not without any load. I'm actually saying under a constant loading.
Okay, sir. There is a statement also called in high temperatures.
That happens in high temperatures. Actually, at high temperatures, what happens is like that's the point.
The point I'm asking.
See, even at high temperatures, you should have some kind of loading, right? Either it can be due to its self weight, or it can be due to some kind of body forces or some kind of externally applied loads. Okay.
When it is in high temperature only, it will possible, na sir?
No, see, creep is actually possible even at low temperatures also, but only its significance is actually less at low temperatures. Whereas at high temperature, for high temperature applications, like for example, you can take off engine materials, right? Materials which are used in engines. So there, the temperature is actually very high, and at those things, creep also you have to take it into account. There you can't neglect creep value.
Yes, sir. What about the time when we come to the high temperatures and low temperatures, sir? It will be reduced and increased while difference in temperature.
See, actually at low temperatures, you will be having some kind of creep value which we can actually neglect for our applications. Okay, for low temperature applications. Okay, so whereas if the same material is subjected to high temperature, then you can't neglect the creep value. Did I answer your question or?
Yes, sir.
Okay.
Yes, sir. Yes, sir.
Okay. Then.
No, sir. It's correct.
It's right? Okay. So here is a problem which is asked in GATE 2016, and here we have given an hypothetical stress strain curve which has three straight lines: PQ, QR, and RS. Okay, and Q is the yield point, and R is the ultimate tensile point, and S is the fracture point. Can you calculate the toughness of the material in megajoules per meter cube? And can you say the answer?
Yeah, sir.
Anyone? I will give you 3 minutes.
Sir, 0.85.
Yeah, 0.85. Yeah. I think you have seen this problem already or worked out this problem already.
Yeah, worked out.
Yeah, okay, fine. So actually here what is the question is like the toughness of the material in megajoules per meter cube, which is actually nothing but the yield, I mean the area under the stress strain curve up to the which point? S or R?
Yes, sir. Yes or R?
R.
Yes.
Up to R or S?
Yes.
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 Up to fracture point S.
Up to point S, you have to calculate the area under the stress strain curve. So you have to take this full thing into account. This full area you have to calculate. Okay, and then you can divide it using this. This can be taken as a triangle, and then this can be taken as one trapezium, and this is another trapezium. And if you calculate the area of 1, 2, and 3 and adding it, you will get finally 0.85. Okay, and the only thing here is like, for example, for this triangle calculation alone, I will show you. Okay, so triangle is like half into base into height, right?
Yes, sir.
So what is the base here? 0.2.
0.2 by 100.
Yeah, 0.2 by 100. This is very important because here you can see the engineering strain which is given in percentage.
it's in percentage. So
Yeah, so we have to divide by 100. Yeah, exactly. And the height of the material is, I mean the height of the triangle is actually 100. Okay.
100.
Yeah. So similar to that, you have to do for the trapezium also, which is nothing but half into h into a plus b. Okay. So h will be around 0.4 into a plus b will be around 100 and 140.
140. Yes.
Yeah. Then again the next trapezium will be around half into h. H will be again 0.8 minus 0.2. I mean 0.6, which will be 0.2. Here I have forgot the 100. So 0.2 divided by 100 into
130.
yeah 140 plus 130. So if you calculate, it turns out to be 0.85 megajoule per meter cube. Since this is actually given in megapascals, we can take it as megajoule per meter cube. Okay.
Yes.
Is this
Okay,
problem
sir.
clear?
Yes.
Yes, sir.
Okay. So here is another problem. So before that, what I will say is like I have forgot one thing, which is the elastic recovery. Okay. For example, imagine this as the stress strain curve of some material. Okay, which is being loaded, and it is like this. Okay. So what happens like so this is the yield point for that material. Okay. This is the yield point. So what happens is like after I'm loading it up to the yield point, I'm actually continuing the loading, but the stress value does not increase, which is kind of ideally plastic material. This kind of material behavior, which we will term it as ideally plastic material. Whereas for example, after the yield point of the curve is like this, means then it is strain hardening, means like we have to provide more yield stress to continue the deformation. Okay. So what I'm doing is like I'm actually loading a particular material up to the yield point, and after that also I'm loading the material, which means I'm entering the region of plastic deformation. Okay. And then after that I'm actually unloading the material. So what happens during the unloading is like it uh, definitely it won't regain its original shape because it has gone to the plastic deformation state. Okay. So after unloading, some little bit of elastic recovery happens, and that path is actually parallel to the stress strain curve under the elastic limit. Okay, it should be parallel to this, and this region or this strain is what is called as elastic recovery strain or the elastic strain. Okay. And this is called as the plastic strain, which is actually uh, seen after even after the load is removed. Okay.
You mean the final strain?
Final strain, yes, final strain. Even after the load is removed, I will get only this much amount of strain. I won't be getting strain up to this because I after the unloading I have recovered some amount of strain. This is due to the elastic recovery. Okay. And this elastic recovery can be found out by sigma y divided by E, which is nothing but yield stress divided by Young's modulus, which is actually nothing but the elastic strain, right? How we can calculate elastic strain? We can take the elastic limit up to the yield point. Okay. And the slope of this is actually nothing but the Young's modulus. Okay. So if you want this elastic strain to be calculated, which is actually nothing but sigma y by E. Okay.
Sir, one doubt.
Hmm.
Can we use the Hooke's law till yield point, because till proportionality limit only we have sigma is proportional to epsilon. So
Yes, bro. But in some applications, what we will be doing is like we will consider the proportional limit up to the yield point.
okay, so it's an assumption as per this
Yeah.
question.
Yes, it's an assumption.
Okay.
Okay. I will check if anyone is joining because I could. Yeah. So now we will go to the next question. Okay. So here you can see a bar of length 5 meter is made of a structural steel having the stress strain diagram as shown in figure. The yield stress of the steel is 250 megapascal. Okay. So here you can see this is the stress strain diagram. Okay. This kind of material is termed as elastic plastic material, which means like it has an elastic region here and it has a plastic region here. Okay. And the yield stress of the steel is given as 250 megapascal. Okay. And the modulus of elasticity also they have given as 200 gigapascals. Okay, and sigma y is given as 250 megapascals. And the initial length of the bar, which is L naught, is equals to 5 meters. And the total elongation, the bar is loaded axially until it elongates 7.5 mm, which here they have given delta L to be 7.5 mm. Okay, and then what they are doing is like they have loaded a specimen of mild steel or steel in a UTM machine, and they have it allowed it to elongate up to 7.5 mm, and after that they have removed the load, and now they are asking like the final length of the bar is being asked compared to its original length. Yes, bro.
So here, the bar elongates up to 7.5 mm, right? So the final L is given.
Not the final L is given. The deformation, the delta L is actually given, because you can see a bar of length 5 meter, right?
Yes, sir.
So from 5 meter, it has been elongated to an additional of 7.5 mm. Okay.
When it compared to original length, it has been increased by 2.5 mm.
No. See, this is 5 meter, bro. This is 5 meter and this is 7.5 mm.
Okay, sir.
Yeah, 7.5 mm is the elongation which you are giving to the 5 meter bar, which means the elongation is very small. Yeah.
So, sir, finally, the elongation is 0.75 mm.
Yeah,
After
recovery. Yeah, the up to 7.5. I mean, the see, for example, the initial length of the bar is 5 mm. Okay. After that, 5 meter plus 7.5 mm elongation I am giving, and then I am unloading it. Is that clear? Is that clear?
Yes, sir.
Yeah.
Yes, sir.
So 5,000 plus 7.5, which means like 5,007.5 mm is the final length. After the yes, bro.
I was saying the final length will be after elastic recovery will be 0.75 mm longer.
No, not like that. You are saying the answer to me or like what?
Answer बता रहा था.
No, bro. Actually, there will be some elastic recovery, and then you will be getting a different answer.
Sir, we have to calculate the residual strain, right, sir?
Yes, we have to calculate the residual strain, and based on that residual strain, you have to multiply this with the original length of the bar, and then you have to calculate the final length.
Sir, 1.25 mm longer आ रहा है finally.
Yes, bro. That is the right answer. Yeah.
1.25.
Yeah, 1.25. Anyway, we will work it out here. Okay. So what happens is like, for example, initially the specimen is loaded up to the yield stress, and then after the yield stress, like it is loaded up to here. But here it is not given whether we have plastically deformed it or not. Okay. So first we have to find the total strain value. Okay. So total strain value can be calculated by change in length divided by original length, right?
7.5 by 5,000.
Yeah, 7.5 by 5,000, which is equals to, what is the value?
1.5 into 10 to the power minus 3.
Yeah, fine. So 0.0015 mm. No, for strain there is no value. There is no unit. Okay. So then, so we have written. So this is the total strain. We will write it as total.
And after
then
that
we have to calculate the yes,
elastic strain.
Yeah, then we have to calculate the elastic strain.
Yes.
Again, there is someone waiting in the lobby.
So elastic strain will be 0.0025.
Yeah, how you are calculating elastic strain value?
The yield strength divided by the modulus of
Yes,
elasticity.
yield strength divided by modulus of elasticity will give you the elastic strain value, which will be, what is the value?
1.25 into 10 to the power minus 3.
Okay, which is 0.00125. So from this, what you can infer? Like the total strain is greater than the elastic strain, right?
Yes.
Yeah. So what we can infer is like plastic deformation has occurred. Plastic deformation has occurred. Sorry about my handwriting. So let's take this as the total strain value, okay, which is 0.0015. Okay. So after I am unloading it, what it will do? It will follow the same curve, right?
Yes, sir.
Yeah. So this is the elastic recovery part up to this. So this I have to subtract so that I can get the plastic strain value. Okay. So the final plastic strain will be how much? 0.0015 minus 0.00125.
0.00025.
0.00025. Okay. And then now I have calculated the plastic strain value, which is the residual strain value, which is existing in the material after the load is removed. Okay. So what is the question? We have to calculate the final length of the bar.
Hello, sir.
Yes.
I have one doubt.
Yeah.
Like when you are calculating like this elastic strain, this strain should be based on the length that exists at that point. Na? Like we are going from recovery, means from loading to recovery.
Yes.
At that time, the initial length was total length was some initial length plus some deformation.
Yes.
So that should be in consideration, na? Or we are only considering the 5 meter length.
No. See, actually, the initial length is actually 5 meter. Okay. Then you are actually elongating it to 7.5 into 10 to the power of minus 3. Okay.
Okay.
And then which means this is the point. This is the 5 plus 7.5 into 10 power minus 3. This is the total elongation. And after that, you are actually removing the load. So during removal, what happens is like some amount of compression happens, or like the total elastic strain which is stored in the material is actually recovered. So the final value of the strain will be around 5 to 5 point, 5007.5, 5000 to 5007.5 mm. Okay.
Okay, sir.
Yeah. So in order to calculate the final length of the bar, what we will do, we know the plastic strain value. So plastic strain is equals to change in length. This is the change in length which we actually need divided by the original length L naught. Okay. So which means delta L is actually nothing but 0.00025 into the original length, which is 5 meter. Okay. So ultimately you will get 1.25 mm delta L, which is actually 1.25 mm longer. Okay. Is it clear to everyone?
So in comparison,
Yes, sir.
you're finding a difference or ratio.
What, bro?
Since they asked in compare with its original length,
Yeah.
so here it's the difference, right? Or
Here is the difference. Yeah. Compared to original length, it is 1.25 mm longer.
Yes, I got it.
Yeah. Again, I could see some people waiting in the lobby. Oh, it's almost 8:10, right? So shall we stop here and shall we see the remaining in the next class?
Sir,
Sir, give us the questions which are left so that we can do it in the next class. We could come forward after solution in the next class.
Okay, okay then. So next, what we are going to see is like a normal and shear stresses, and then why complement, how we can show the complementary shear stresses are equal, and then what is the matrix representation of stress. So maybe you can note down this problem.
So we'll take screen. I have taken a screenshot.
Okay,
You can.
okay then.
Yes, the next question.
Move into the previous.
Yes, bro. Your voice is very feeble. I couldn't hear you properly.
Okay, could you please move into the previous slide?
Yeah.
Like, yeah. This one.
This one. Okay.
No, actually, the next of that problem. Next slide of that problem. Yeah. Okay.
Okay.
Yeah.
So in the next class, we'll be working out some problems, and we will be seeing about the axial loading, the relations between the elastic constants, the difference between pressure and stress, and how we can represent stress and strain as a matrix. Those things. Okay.
excuse me, sir.
Yes, bro. Yeah.
I'm sorry, sir. Whatever question. I have one question, sir. Please.
Yes, bro.
Sir, what is the weightage of the subject, sir? How many marks in gate examinations are in strength of material?
It actually varies from, we can say, 6 to 10 marks, I guess.
Oh, okay, sir.
Yeah.
Thank you.
Yeah.
Thank you, sir.
Yeah. So since this is my first class, this is my first online session. Like I'm handling NPTEL live session. So actually, I'm not used to these kinds of classes. So today I went very slowly. Maybe in the upcoming classes, I will be working on those things, and I will be.
No problem, sir. You're doing great. You're doing good, sir. Great, sir.
Okay. Thank you.
Okay, thank you.
So is it fine?
Can you explain that elastic recovery part?
Elastic recovery part. Okay. That's what, bro. See, actually, what we are seeing is like, this is the stress strain graph, right? So we are actually having a material which is loaded up to here. Okay, imagine, huh? This is like an elastic plastic material with strain hardening, which means like the yield stress values increases with strain. Okay. So what happens here is like, for example, after the yield stress has been crossed. Okay, after I have crossed the yield stress, and again if I am continuing the loading conditions, what happens is like the plastic deformation starts, right?
Yes, sir.
Okay.
Entered plastic region.
So it has entered the plastic state and the plastic deformation has started. So after the removal of, for example, I have reached up to this point, and then what I am doing is like I am removing the load entirely, all of a sudden. Okay, or gradually I am removing the load. So what happens is like, it won't stay at this point, or the final dimensions of the specimen, it won't stay here. Rather, it actually recovers some of the, because in the material both the elastic as well as the plastic strain is stored. Okay, so elastic strain is actually recovered even after the loading conditions. Okay, so that elastic strain is actually, elastic recovery path actually follows the original stress strain curve up to the elastic limit. So parallelly it will come up to here. Okay.
So there will be some elasticity happening.
Yeah. There
with
will be
effect
some
of
kind
plasticity.
of spring back effect. In simple terms, if you want to imagine, like take a rubber band. Okay. After that, it is rebound. I mean, it is compressed, right? After you remove the load.
Yes, sir.
Yeah, but in rubber band fully you are getting the recovery, whereas for normal material you won't get full recovery. Only the elastic strain will be recovered, whereas the residual strain, which is the amount of plastic deformation which you have given here, this actually remains the same.
That effect will remain same.
Yeah, that effect remains even after the loading.
But the slope remains same, right?
The slope remains here. The slope remains same. So due to this slope only, you are actually equating this strain value to this strain value, so that ultimately the residual stress, which is or the residual strain, which is actually inside the material, is actually nothing but the plastic strain.
Yes.
Am I clear, or should I have to explain it again?
It's clear.
Okay. So we will see the remaining things in the next class. Okay.
So the next class will be the next week.
Next week, yeah, next Monday.
Sir, we have a session planned till the exam time, sir.
What, bro?
We have these sessions planned till the exams.
Yeah. Up to January 23rd, they have given us these slots. January 23rd week.
Thank you, sir. Thanks a lot.
Yeah.
Thank you.
Thank you.
Thank you so much, sir.
Yeah.
If
Thank
you
you.
don't mind, could you please, sir, excuse me, sir.
Yes, bro.
Sir, can we view the recording of the today's sessions later, sir? Because I could not connect at right time, sir.
Sure, bro. Next time I will also try to inquire about this auto admit, and then I will try to figure it out, and then I will make this video also available in the YouTube. Okay.
Thank you, sir.
Also, can you give this PDF also so that we can do the questions?
I mean the question problems alone, right?
Yeah.
The workload problems, like you can see from the YouTube video itself, whereas the remaining problems, I think it would be better if I actually solve these problems in the class once after taking these concepts. Is it fine?
No problem.
Yes, sir. Yes, sir.
Yeah, maybe from the next class we will try to figure it out, we will try to work out more problems. I will give you some more homework problems also. Okay.
Yes, sir.
Okay.
Yes, sir.